All right, so let's get a taste for what one of these cycle videos is going to look like, where we delve into one particular historical cycle and we study the nuts and bolts of it. So the cycle that we're going to study today is called the reverse Brayton cycle. So that's how Brayton is spelled. And there, as you can imagine, so this is the reversed version of the Brayton cycle. And so the Brayton cycle itself is a heat to work cycle. We're looking to use the natural heat flow from hot to cold and pull work out. The reverse Brayton cycle is the reverse version of that. In other words, the cycle's flowing the opposite direction, where we're looking to put work in and make heat flow from cold to hot, or the opposite direction of its natural flow. All right, there's a special other name for the reverse Brayton cycle, and that is the Bell-Coleman cycle. There was just a lot of people involved in discovering these cycles, okay? Let's see. The basic format of the cycle is this. 1. Isentropic compression. So that's a compressor or a pump or anything like that. The second one is isobaric heat addition. And this takes place in a condenser. So this is also condensation. We're lowering the volume as we do this, but it's isobaric, so it's at a constant pressure. The third step is isentropic expansion. Opposite of compression. And then the fourth step is isobaric heat removal. And this is in an evaporator. Okay, so this is the basic steps of the reverse Brayton cycle. If you wanted to study the Brayton, you would do the exact opposite. And again, we talked about this, you'd have to build a whole different machine, because there's an actual physical part in this to do each one of these steps. And you would need the part that does the opposite of this step in order to build the Brayton cycle machine. So these steps are for the reverse Brayton cycle machine, or the Bell-Coleman machine. Now, as always, we're going to track the progress on a nice big PV and TS diagram, okay? And we're going to look at what's happening to the different points. The first thing that should be noted is for the PV diagram, we can actually sketch in a familiar shape. We're pretty familiar with that. This is the saturated liquid line, and this is the saturated vapor line. Okay? And then in the middle is the mixed state. On this side is liquid, on that side is vapor. You've had this on tests, you remember this. Okay? So let's sketch that in. You may remember that last time we listed all the cycles, and we didn't list the Brayton cycle as one of on our list. What we listed was the Rankine cycle. And the Rankine cycle and the Brayton cycle only have one difference. If the cycle happened all out here in the vapor phase, and it didn't cross the boundary at all, right? It had nothing to do with the mixed or the liquid, everything was vapor. This would be Rankine, okay? So let me make a note of that up here. Actually, that's gonna be a busy place. I'll make it over here. All vapor cycle would be the reverse Rankine cycle. So we're not going to get a special video on the Rankine cycle by itself. This is the Rankine cycle, basically. I'm just going to move it over The Brayton cycle is a little more complex because instead of happening all out here in the vapor, it's going to happen in the mixed region. And so there's actually going to be phase changes. Okay? So reverse Brayton, reverse Rankine, that's the only difference. So let's go ahead and get started plotting some points on here. So the first thing that we're going to do is start out here in the gas phase. And this will be point 1. And we're going to be at a pressure P1 out there, okay? And this corresponds with some point out here in TS space. That's also, well, let me lift it up a little bit. Okay, that's going to be state 1. Then we're going to isentropically compress it. So what the bar for that looks like, we know there's a little compression, so the volume shrinks back, but we know that definitely the pressure jumps up. So we're going backwards in volume, backwards in pressure. Turns out that we get something like this. And this goes up to state 2. Now on this diagram, and we've gone this way. Let's mark our direction with little arrows. Over here, it's isentropic. That means constant S. There's no deviation or change in S. So this just goes straight up. Okay? That makes sense. Isentropic, constant S. For the next step, we have heat addition, but it's at isobaric. So our pressure is constant. So here's what we get. Notice that we're crossing phase transition lines, okay? And I'll mark the little arrow to show the direction. We go from 2 to 3, and it's flat on this diagram because it's at constant pressure. But what does it look like over here? Well, if I draw from 2 until we hit this boundary, we know that we can picture that 3-dimensional surface. We're going from here to here is changing the temperature. So we know that the temperature is dropping, okay? This was state 2, this is state 3 over here. Temperature is dropping down. And I want to draw this a little bit more curved. As to why exactly those lines are curved, you need calculus to show that, okay? But it's a little bit curvy. It arrives here on this diagram when it hits the phase boundary. Then you'll remember, across this mix region, it actually arrives somewhere like this, right? There's an intermediate point that it hits there. Then across this mix region, as the pressure is constant, the temperature is also constant. So it's just chilling here, hanging out, as we're adding heat to go across, okay? Okay. I just want to make sure that I have this right, because that seems like we're losing heat. I think I might have it backwards, the heat removal and heat addition. Let's see here. Yeah, this is backwards. So it's a good thing I caught that. So change it in your notes. Yes. We're all good now, okay? So heat's being removed as we go across here. And then we hit this point, it's constant again, it's just chilling here. And then when we hit this liquid line, therefore now the temperature decreases again. So we go all the way to our state 3, okay? But across this transition line, the temperature is just waiting at that point as we keep losing heat to have that phase transition. We're losing what we would call the latent heat, like we've talked about. Okay, now we have the same thing, but backwards. We had compression, now we have expansion. So this is going to be an angled line back here to state 4, okay? And we want state 1. I just want to make sure I draw this right, so that, oh, and this is isentropic. So we have the entropy dropping, okay, down to state 4. And then from 4 to 1, we have this, and then it's also isobaric, right? We're adding heat, so we're again crossing this phase transition, and then this thing doesn't change the temperature at all. So as we're going across here, we're at constant pressure, so in the mixed state, we're also at constant temperature, so we're just chilling, waiting, and then once we hit this point, now the rest of this way, right there, that's when the temperature goes back up to there, okay? So, oh, and this pressure up here, we can call this P2. So there's two pressures that it goes between. And that's what the cycle looks like, okay? This is the reverse Brayton. Again, if we were out just in the gas doing this whole thing, it would be Rankine. But Brayton is the one that actually crosses phase transition boundaries. All right, so also I'm gonna mark these 4 temperatures. So this was T2 up here, T3, T1, and down here T4, because those will come in right here in a second. Let's make an approximation, okay? We want to figure out how much heat is lost here and how much heat is gained here, okay? This is where it's removed, this is where it's added. And I'm gonna do a cheater method that can kind of work. So it's not really, but we can do Q equals MCP delta T for the heat loss in addition, because there's 2 different temperatures here, right? So from 2 to 3, we can just track T2 minus T3 and use our delta T. The reason why it's not really is, again, this is across here changing state. So it's somewhat in the gas phase, which this doesn't work for. So this is an approximation. The real thing we should do is use the enthalpies. This is the thing we just learned about a couple lectures ago in the lookup tables. So as we discussed, the actual numbers, you just find them in the lookup tables. But that's not very satisfying, and this gives us a lot more like theoretical purchase as far as actually getting stuff done here, okay? So if I change out each Q for a delta T, so my Q high, or my heat that is removed from the system in the high one, that comes out to be the difference between T3 and T2 times MC, and my Q low is the difference between T4 and T1 MC. So see how I can make those substitutions and use temperature differences to calculate my Qs. Therefore, let's look at the Brayton cycle. Now remember, the Brayton cycle would be the reverse of this. So we went this way, around, clockwise, like that. But in the Brayton cycle, we would go like that. We would take this whole thing, we'd have a different machine built to do the same cycle in the other direction. And in that case, it would be a power cycle where we're getting work out. And so the thing we would care about is efficiency. This is eta. And this comes out to 1 minus, and then the temperature differences. Okay? Yeah, this should be T1 minus T4, absolutely. It can be the other way around, actually, depending on how you do your sign conventions. So one will give you a plus, one will give you a minus. So if you plug in Q low over Q high, you'll notice that the MCs cancel in this equation, and we get this for efficiency, okay? And then for reverse Brayton, that's still the efficiency, but the efficiency isn't what we care about. We care about the coefficient of performance. And we'll look at the refrigeration one. The reason we use the refrigeration one is that this is the cycle that we can use to model what refrigerators do. Refrigerators and AC units. They're both basically the same thing, okay? They do the same job. The AC unit pretends that the whole room it's in is the refrigerator. And this is one of the cycles that we can use as a theoretical model for how an AC unit works, all right? So that's why we're using the coefficient of performance refrigeration, because what we care about is how much heat we can pull out of the cold place, okay? In the case of a room, the cold place is the entire room. So this is going to be an important formula, the coefficient of performance. And now let's talk about what the numbers would come out to. Well, in this ideal case, we did isentropic here and here. That means perfect, right? No entropy is generated. There's no entropy change. So what that would mean is that this gap in temperatures, the gap between 1 and 4, is the same size as the gap between 2 and 3. And what that means is that that number and that number are the same. So whatever they are, they cancel to 1. Now look what we have. 1 over 0, because this is 1 minus 1. In the bottom, you get 0. So the perfect ideal, the coefficient of performance equals infinity. That makes sense because isentropic means perfection, which means ideal, which means it can't actually be achieved. This is perfect, and the coefficient of performance is going to be the best possible. That means that we have free heat flow in the wrong direction, the unnatural direction, without having to put any work in. In the real world, how we can modify this is that, like I talked about, those lines that we said are isentropic, meaning they're straight up and down. There's no deviation. So as we go along that process, the entropy doesn't shift or change to the left or the right end. But in the real world, what we could have, let me extend these curves a little bit, is starting here, we get ran out of storage space, guys, at the end. All I was saying is that when we get skewed off this main path, we intercept this curve at a higher point. So there's this T2 prime, or this imperfect higher temperature that we go up to over here. And the same thing happens down here. Instead of a straight line down, we get a little bit skewed off this way into intersecting this curve at a slightly higher point, so a slightly higher temperature, T4 prime. And that changes the gaps between now T1 and T4 prime. That gap shrinks a little. And between T3 and T2 prime, that gap expands a little. So now those two differences, the difference there and the difference there, are different numbers. And so these being different numbers, you don't get infinity anymore. You get like an actual calculation with a real non-infinity, non-zero number out the end. And in the real world, for air conditioner units, the coefficient of performance is in the range of 2 to 4, okay? So this is the reverse Brayton cycle. It's essentially the same as the reverse Rankine cycle, just with a phase change in it. Also called Bell-Coleman, and this is what we use as a model or a theoretical picture of a refrigerator or an AC unit.